Okay, welcome back. And this is the second half of the lecture. We're supposed to finish already this first lecture after this session, and hopefully I will be able to finish the entire lecture one and start with a new lecture before the end of the lecture today. Okay, let me share my screen. It's recording, right? Yes, it's recording. And I want to share my screen. Okay, so now we are going to give an example of how we are going to apply this. So we say that this is the data. Normally, data is given as a table. Yeah. So table of inputs I. We are saying that there's I as there are 6 data points. So you have 1. Your I goes from 1, 2, 3, 4, 5, and 6. Okay. So I don't know how it looks like. Maybe it will look like this. I don't know. Okay, let's see. Okay, so when x is 0, 0.1, 2, 3, 4, 5. Okay, so 0, 0.1, 0.2, 0.3, 0.4, 0.5. Okay, so 20 up to 70. So let's just say this is 2, 4, 6, and 8. So this is 20, 40, 60, and 80. Okay. So now at 0, you have, okay, what do you have? Okay, at 0, you have 20. Okay, 0. At 0.1, you have 30. So here, at 0.2, you have 50. Here, 0.3, you have 60. Here, 0.4, you have 70. Here, around here. 0.5, you have 20 here. Okay, so the graph looks like this, roughly. Okay, so what kind of graph can we, what kind of function can we best approximate this kind of data? So it looks like parabola, yeah, but somehow it's skewed a little bit. Okay, but anyway, we want to estimate this data, these data points in terms of a parabola. So you have a second-degree polynomial. Understand? So because we want to know that parabola, we need to know what are the values of W0, W1, and W2, okay, that best fits this parabola. Again, I want to remind you that there are many parabolas that can, this one, that one, that one. Let's just concentrate on this kind of parabola, hill parabola. Okay, so there are many types depending on your W1, W2, and W0, W1, and W2. Okay, so we will see which parabola best fits this one by looking at the error functions. Okay, now, next. So, okay, we clear everything. Okay, so we just input into the equation. Okay, so here, this is your T. Okay, and this is your Y, W0. Okay, xi to the 0. This is W1 xi to the 1, W2 xi to the 2. Okay, well, because your W's are already here, so that means that we can get rid of the W's here. Okay, because when you multiply, this is already the summation. You understand? Multiply this one against W1, so that's this part. Okay, xi. Okay, xi is equal. Your I is the point here. 1, 2, 3, 4, 5, and 6. The same thing here. You have your I is here. So 1, 2, 3, 4, 5, and 6. Okay. So this is your target value. That's the result of the computation. Okay. So you just write it down 20, 30 up to here. Okay. So the first function is W0 multiplied by xi to the 0. What is xi? That's 0 to the 0. This is I here is equal to 1. Okay. 0 to the 0, that's 1. So this is just 1. Okay. Now W2 multiplied by xi. Xi is this again, 0 to the power 1. So that's 0, 0 to the power 1. And then W2 multiplied by xi. This is 0, 0 to the power 2. So done. This is the first part. Any questions? The next point, second point. Okay, the output is 30. Okay, this is 30. Okay, the target value is 30. And then our polynomial function is W0 multiplied by 0.1 to the power 0. But the point, any number to the power 0, that's 1. So this is W0 multiplied by 1. Next, W1 multiplied by 0.1. 0.1, because this is your xi, 0.1 to the power 1. So 0.1 to the power 1 plus W2 multiplied by 0.1 squared. So that's the second point. Any questions? And so on. Will you repeat? Because what's happening here is that you have the target value. Okay, this is your target output value. This is your polynomial function. Okay, polynomial function for each of the given data. Okay, given the W0, W1, and W2. Okay, now we don't know this value, but we know that for the polynomial function, its output should be 20, given an input xi equal to 0. For a given W1, W2, W3, its output will be 30 when your xi is 0.1. There. Next, your W0, W1, W2 will become 50 if your input is 0.2. Again, 60 if input is 0.3, 70 is input is 0.4, and 20 again if the input is 0.5. Okay, so we are just writing the target value versus the polynomial function that will try to estimate this output that is the target value. Now, so there are two ways of computing this. One is analytical method. So in this case, we are doing analytical method where we know from your linear algebra, or you have linear algebra or numerical methods, we say that x, okay, numerical algebra is that x is equal to, what is that? A times some value t. Okay, or okay, maybe those are confusing. Okay, y is equal to a times x. Okay, that's the input and the output, or in this case here, the output is t. We can say t, okay, given some matrix A multiplied by the input x. Okay, so in this case here, your x is, okay, in this case here, this is t multiplied by your x. Your big X is actually these values of the x, and then now it is w. Okay, that's w and the target output t. So in this case, this is your t. This is the value x, input x, and this is your w. Okay, so now because we want to solve for w, so we take the inverse. So we take the inverse. So from w, okay, from T is equal to X times W now becomes, you take the inverse of that, so becomes W is equal to X inverse times T. Now you can compute your W directly. Finish. You can run MATLAB. You can now look for W. Okay. Okay, sir. Yeah, then it's fine. Well, then why do we need to do some numerical, some other estimates when we can easily compute it? That's a good question. Why? Why do you think? Well, MATLAB can already use this. Matrix inverse can already do it. Why do we still need an estimation like what we are doing? We want to compute W's in a certain way by the error term like that, estimates. Why do we need to do that? When we can easily, our mathematical tools can already compute for it. How many?
If we're implementing it.
Yes, who's that?
Mopati.
Mopati. Okay, Mopati.
I was saying if we're implementing it from scratch, then we can only use numerical methods in a computer. A computer only does numerical methods.
What about the solution? Is this not correct?
No, the solution is correct, but to code analytical method into a computer is tedious.
No, it's just 2 lines. You just equate X is equal to this matrix. Okay. And then T is equal to that matrix. X inverse times T, compute W. Okay, I'll show you. Okay, I'll show you on how easy it is. Okay. Just so you can have a feel of what's going on. Okay. And we need to know, and also to appreciate the reason for why we still need to do it when our, where is this octave? How come it's not showing? Yeah. How come our, okay. Okay, let me do octave. Okay, so here we go. Let's just write the whole thing so that to convince ourselves. Okay, so T, okay, T is equal to this value here. Okay, that's 20, 30, 50, 60, 70, and 20. Okay, okay, and then transpose. So that's your T. And then your big X is equal to 1, 0, 0, okay, semicolon, 1, 0.1, 0.1, and then 0.1 squared, okay. The other one, is it 1.1 and 0.1? Yeah, please tell me if there's any wrong inputs I did. And then power 2, okay, and then 1, 0.3, 0.3, power 2. 1, 0.4, 0.4, power 2, and 1, 0.5, 0.5, power 2. Okay, so that's your X. There, that's your X. Now, let's compute W. W is equal to X. Okay, inverse. What is inverse? I think inverse like this. Multiplied by T. Okay. It's not a P inverse. There. W, 12 minus 340 minus 607. You see it? So what's the use? We're just making, I mean, is it because we want to make our lives difficult? There. We input your T. We input your T, your X, and that's your W. We can compute easily. Okay, T, your X, and your W is equal to Again, P inverse of X times T. Finish. Okay? So that's your T, that's your X. Now, why? That is just how many lines of codes? 2 lines of codes. Assignment of T and X, and 3. And computation of W. Why do we still need to do numerical computation when we can do analytical? No? How ne?
Can you explain the numerical method first?
Numerical method, our estimates. Numerical method is this one, computing for the W. We want to estimate our W. Okay? We want to estimate what is the value of the W, the function, using our estimation of this iterative computation of W's. So where we initialize a W some value, compute with respect to the error, compute for the new W, compute for the next error, compute for the new W. When we can just have to do this and no need to run through this algorithm. Okay, I will give you an answer. Okay, because we want to make our lives more difficult. Okay, well, it's not worth studying if your life is not difficult. It's part of your training. That's one. The other one is that this matrix can be very, very big for real world computations. Okay, and sometimes maybe MATLAB cannot do it anymore. That inverse of 100 by 100 matrix, MATLAB will have difficulty computing that. Okay, but because we are doing in this case we are doing an iterative manner. Okay, we adjust the weights. Every time it is just the same cycle of computation, just adjusting the weights. Okay, you adjust the weights until it becomes closer and closer and closer to the actual value. To closer and closer until the error can become much, much smaller to the actual data that was given. Okay. Okay. Now, how are we going? The question is, how do we do numerical methods? So this is numerical. Yeah, I didn't tell you exactly how it is being done before this, but now this is how do I get rid of this window? Okay. Anyway, it's not. Okay. So let's continue. So in this case here, this is the method. So this was the analytical method that we used previously, and now this is the numerical method. So given the same data set, we are now going to find the W's that will make our polynomial function as close as possible to these data points. Okay, so initially at the very start, we will have our random values of W. So we don't, there's no right or wrong answer. This is just good and better answers. Okay, so here we initialize W. Okay, so W can be, I don't know, 1, 1, 1. Okay, it's up to you. Okay, and then next we compute for the gradient. So we compute for this, whatever is the value of W multiplied by the input. Okay, for each line multiplied by the input X minus the target value, multiplied by the input X again to the power of I. Depending on what your I is, your I goes from 0, 1, and 2. 0, 1, and 2. Okay, then afterwards you compute this with respect to W1, okay, W0, W1, and W2. Now this is the error function. It will be much clearer on the other side after this slide. Multiplied by this step size, normally around 0.1. Okay, now your current W that you initialized you minus with this step size multiplied by the vector of the errors to update your new W. Then you repeat until your error term becomes smaller. So if you achieve around almost certain threshold of the error, probably around less than 0.01, for example, then you stop computation because you are close already to the correct value. Okay, so how? Okay, this in principle, this is what we do, but then we continue on this one to show the actual example. So we initialize W1, W2, W3 equal to 1. So that's given. Now we compute the gradient. So this is the most tedious part. The gradient of error minus the gradient of error W with respect to W0. Gradient of error W with respect to W1. Gradient of error W with respect to W2. So because there are 3 W's, yeah. So you have three derivatives with respect to each W term. Okay, now how do you go about it? So again, this is this is just W, okay, W0, this is W0, W1, W2, okay, multiplied by XI 0, XI 1, XI 2 minus TI multiplied by XI 0 because it is a summation. So XI 0 up to XI, in this case, this one should always be 0 because we are computing with respect to, this is always 0. Okay. And because we're computing with respect to W0. This one is always 1 because we are computing with respect to W1. Okay. And the rest of them will be the same. Okay. You see, this is the same as this. So that means that if you have computed all these terms inside, this term, this term, this term, if you computed all of them, all you need to do is multiply each term against this XI value for the power 0, for the power 1, and for the power 2. Okay? There's many things that are repeated. So you can just, make this one into a matrix form and then multiply by this vector. Okay, then you can get what you need. Okay, so anyway, so go ahead and try to do it yourself. Then you can find a value of this error. Now, given the value of XI, okay, with the current value of W1, W2, and W3. Because here you have W0, W1, and W3. So here is always 1. So 1 times 0, 1 times 0, 1 times 0. So 1 times 0.1 to the 0, 1 times 0.1 to the 0 to the 1, 1 times 0.1 to the 2. Because this is the exponent. Okay, this is polynomial, and then you have the same. You have the same inputs. Okay, the same input as that. Okay, this one, same inputs. It's there. This one, same inputs as there, like that. Okay. Like that. Okay. So these are depending on your data inputs. Okay. Please remember that. Another data input. Each line will be dependent on the data input. There you go. On the 5th line. Now, the other ones that you have to remember is the order of the polynomial here, order 0. Okay, order 1 and order 2. Okay, and these are the targets based on the corresponding data points. These are the targets. Okay, so like that. Now multiply it with your, again, multiply it with your input data to the power 0, because this is 0. So input data, input data, input data, input data, data, input data. Okay, so hopefully that's clear. There's, the lines are very unclear, but hopefully with the motion, you know, it helps you which one, which one is corresponding to the points in the data set. So now, because this is, again, this is W0, that's x to the power 0, xi to the power 0, W1, xi to the power 1, and then the same thing inside, you have xi, the same thing, xi to the power 2, because you're considering W2. Now you'll have three values that you compute here. One value partial with respect to W0, W1, and W2. So partial with W0, W1, and W2. Now you have three values multiplied by the learning rate, and then this is 1, 1, 1. So this is 1, this is 1, and this is 1. Now you have a new value of W computed from here. Okay. Afterwards, what do? You go back here, and then now you have new sets of W. It's the same equation that now the W, instead of everything 1 year, you change it to the new values of W. The same thing applies because the data set don't change. Only the W's change. Then you have new value W1, error W with respect to W0, error W with respect to W1, error W with respect to W2. Now you have new values of the error, of the gradient of the error, multiplied by the learning rate of this new value of W. Then there's a new, after this computation, there's new updated value. Use that again, and then come back here. Come back, same thing, until your error is minimized. So probably you can say until WE with respect to W0 is less than 0.01. Okay, and something like that, yeah. Partial of E with respect to W1 is less than 0.01, and like that. Partial of E with respect to W2 is less than 0.01. Okay, and so on. Until that time didn't reach, then you continue. Or sometimes if it doesn't converge, meaning it doesn't reach this, you can say that until iteration, yeah, maybe you have number of iterations greater than maybe 1,000, then you exit. Okay, so again, the advantages of this is that it can compute as many number of data sets as big of a matrix that you have, because it is just continue computing based on how many input data you have. But for the matrix in MATLAB, it's dependent on, I mean, the size of the matrix. The MATLAB will have a hard time computing the inverse if the matrix is very big. But here, there's no problem with computation. Just continue iterations until you reach a certain number of error value and a certain you reach the maximum iteration. Yes, Haune.
I didn't hear what you said. How do we stop the iterations? When do they stop?
They will stop when there are two times that you stop. There are two cases that you stop iteration. First, you stop iteration when your error term, this one, is less than 0.1. Let's just say that the norm, you can see, of the error, okay, is less than 0.01. Or in this case here, I'm saying about the rate of change, the gradient is become less than 1. That means it's getting flatter and flatter. The gradient becomes flatter and flatter. It's fine. Or the error becomes smaller and smaller. So what is the norm of the error? That means the error of W with this error W, the first term, squared, error of W, sorry. Second term, squared, you add, that's the normal way of computing for norms. The third term, squared, then the square root. That's equivalent to this one. Or easier way is that this one, each of the term, say less than 0.01. Okay, just check this one. Okay. Okay, depending, in this case here, you're looking at the gradient, that the gradient can almost become 0. So that means getting flatter and flatter. Okay, here the error becomes smaller and smaller, or maybe less than 0. Okay, and the other one is about iteration. So remember that you're iterating. Yeah, you update W every time. So you start with initializing W, compute your error. Okay, and then update your W's. Okay, once then this is the first update. Then repeat. Okay, you repeat and then go to the next update, second update. Okay, then repeat, go back, repeat the third update, and so on until you reach maybe 1,000 iterations. Okay, if you reach 1,000 already, greater than 1,000, you better stop. You're not going anywhere. Okay. Just like you're asking someone to borrow you money, and you reach already 1,000 requests and still it doesn't let you borrow money. There's no way it will borrow you money very soon. Yeah, so you better stop. Okay, you go to somebody else who might likely give you money in the first request. Okay, so please I think this is more clear when you run the laboratory exercise. Okay, questions? No. Now is oh, it's late already to start, but I'm in a good time. Okay. We'll start, I think 46, it's fine, 15 more minutes. So that's okay. I will stop here. I think I will answer your questions if you have any, so that we can go to the next lab. Okay, can go to the lab exercise. Well, I can open the lab exercise for you if you have any questions. We can discuss that. This is labs. Okay, let me look at my book. Manual. Okay. Ah, that's not the one. The one that's really nice. Where is the one that's really nice? Here. Ah, this one. I draw the cover myself. Okay. Okay, so that's your laboratory manual, and you go preface and all these other things. I have ISBN now, I can put it. Okay, then now lab exercise 1, 2, and 3, and 4 up to 8. Okay, then you have all the lectures there. Okay, then we can go to about the author. There, yeah, that's the last page. There's a back cover. Okay, then the abstract about the book, and that's me. Okay, now let's go back to the exercises. A lot of things here are the lecture slides. Okay, so just maybe 9 pages, the exercises. I will add more items to this one, but for now, that's the lab exercise. So now we have done already. We have done this one, laboratory exercise number 1, number 2. So this is the one, polynomial function. So let's concentrate on this. I will just add a little bit of question for you to analyze the data so that you will have, you can upload something besides the write-up that you will be doing. So now you say sine of 2 pi x. Okay, that's your function. And the polynomial is this one. Okay, so now use a polynomial 6, n is equal to 6, to approximate the function of sine 2 pi x without noise. Okay, what does it mean? So your x goes from equally spaced points. So you design your x, x1, x2, x3, up to x, okay, up to 6 data points. So what do you do that? How do you do that? So again, you have I, okay, 1, 2, 3, 4, 5, 6. Okay, your xi will be 6 data points. So you can have 0.1, or maybe 0 starts with 0.1, I don't know, 0.2. If this one is a bad x points, maybe this is quite bad data separation, then maybe you increase it a little bit. I'm not sure. Then the target is that you compute based on sine of 2 pi x. So t will be sine of 2 pi of whatever is your x here, 2 pi of 0. So this is 0, of course. X is sine of 2 pi of 0.1 times like that. 0.1 is equal to something. Okay, now you have all these 6 points. And now those are your data sets. Now you need to compute your m is equal to 3. So up to here, w 3 x to the 3. Then remove this. Okay, that means m is equal to 3. Okay, so now we need to compute 4, w1, w2, I mean w0, w1, w2, and w3. Okay, find the optimal value. Oh, how come this is w2? I said, I think there's something wrong here. Okay, because I only asked for up to, maybe this is a mistake. Okay, never mind. Let's just do until 2. Okay, that's to make your life easier. Okay, so let's cancel that one. So we make this one up to there. Please listen, okay? Just make, because this is my mistake here. You see, I only asked W0, W1, W2, but then here m is equal to 3. So it should be, let's just follow this one. So your life will become easier. Okay, now this is your error function, and this is your gradient of the error. So you start, it's here. Okay, the other way around, sorry. Because now I write W0, okay, this one is the one that's wrong. Okay, I thought, okay, here it should be up to W3 star. Okay, normally when you have a star for a W, for example, that means it is the optimal value. Optimal value of the weights, you have W star. Okay, now optimal meaning the error becomes small already, or you reach certain number of iterations. I mean, it's not optimal yet when you reach number of iterations, but when your error is becoming smaller. Okay, that's the optimal value. Now, so this is your error term, and you compute your error based on this. Okay, the gradient of the error. So you compute the gradient of the error. You input here, multiply it by this one. You can initialize it based on just 1, 1, 1. That's fine. Okay. Now, based on this computation, you'll look for the new W's and repeat. Okay. So based on the new W, you compute the gradient. This one, new W, compute the gradient. This new W, and then update again, and so on. Okay. So first, there are things that you need to do. Okay. Perform hand computation for the problem up to 3 iterations. So what is 3 iterations? Iterations meaning the first iteration, okay, iteration 1 is when you have your initial values of W. Okay, initialize your W to some value, maybe 111. That's the first iteration, iteration 1. Okay. Once you finish this, you get a new value of W, right? So iteration 1, iteration 2, new value of W from there. So I don't know what's the value there. So when you compute the new value, that will start your iteration, second iteration. Okay. Now you compute another W. Okay, that is your third iteration. Okay. So after the third iteration, you will have a new value of W. That will be your W star. That's the best W that you find. Okay. So every iteration 1 here, you output W2, right? So on W2, you output W3. Okay. On W3, you output W star. So that's what I mean. Normally, the students have a problem here. How many iterations you have? So iteration 2, iteration 3. Okay. That means that when you say number of iterations, that means you compute 3 new values of W. Okay. 3 iterations, 3 new values. Okay. Based on initial value, you compute new value, initial value, this new value, compute another value, this new value, like that. Yeah. 3 new values. Okay. I hope that's clear. Okay. So now here, compute 3 iterations, they're computing 3 updated values of W. So 3 updates of W. Draw the polynomial with the final values of W. This is important. Manually draw. Okay, draw by hand on how your polynomial looks like versus the function of 2 pi x. Okay, so you will have like that. So 2 pi x and your maybe this is parabola, yeah. Oh no, this is cubic. Okay, so this is your y of x. W. You draw. You follow all the instructions here. Another 50 points. This is 50 points, okay? Use programming. Now, you use a MATLAB to compute. Okay? In this one, MATLAB, I expect you to copy and paste your code into the paper. Okay? This one is manual. Okay? Do you know how to combine them? You scan and combine them. Okay, or maybe you make your drawing and then put it in the Word file. Yeah, just in the Word file, and then this programming code you put in the Word file as well. Then what will this Camela? What she will do is that she will copy your code and run it in MATLAB and see if it works. Okay, so there are 2 areas that you will be graded. 1. Okay, never mind for now. I thought there's everything is by hand. Okay, so no, so now there's no extra. I don't need to give you extra exercise. This is good enough already. I think that's too much already if I give you some more extra. So do the manual computation, take a photo and then paste it into Word document. Here, do a program in MATLAB or Python or Octave, because Octave here I'm using Octave, it's free. Okay, and then you paste it into Word, and then Camela will check. So you get 50 points, half, 50 points for the manual computation, 50 points for the program. Remember, also in the program, you need to plot the polynomial. Plot it using the MATLAB code, okay? So in your code, when Camela runs it, it will come out with a plot. Any questions? We are going to the...
Can someone use Python? Say someone prefers Python.
Yes, you can. You can run Python. Anything, it's okay. Okay, just tell Camela on where to run it, you know. It's a platform for Python platform, where to run it, and then she can run it. It's just a matter of executing it in Python.
Okay.
Okay. Okay. Anything else? Are all of you okay with programming? Okay, Mupati must be very good at programming because he's, you know, wanting Python. Okay.
Of course.
Okay. Then I will give you more work to do. Anyone else wanting a question? Okay, so next meeting tomorrow, I will give you the exercise today and then submit it. I hope this time in the submission of Turnitin, you won't have a problem. Those of you who still didn't submit, please submit. Okay, if it's already closed, ask Camila to open the submission. It's okay, extend the submission for now. It's fine, but next time I will be more strict. A week after the submission deadline, if you still didn't submit, you cannot submit anymore. Okay, but normally that's what I do. I open the exercise for 1 week for you to submit. Okay, and then afterwards, that's the deadline, 1 week deadline. And then if you are late, you can submit in another week, but there's a deduction. Okay, but beyond that second week, no more. You cannot submit anymore, so you get a 0 immediately. Okay, so my advice is please finish as early as you can and submit. Don't wait until the last minute. The software knows that you are having a hard time. And you know how life is. When life knows that you're having a hard time, it will give you the hardest time of your life. That's how it is. Because if you don't have it, life will be so boring. You know, that's why life is so beautiful. Yeah, it knows when it will really pull you down to the ditches when you need it most. Yeah. Okay, so tomorrow we'll start with a new topic of decision trees. Okay, I plan to cover 3 topics. Okay, for these 3 topics just before for your long test. Okay, I will discuss when the long test, but the long test will be the week. I mean the class time before the break. When is that? That is 2021. Here, our mid-semester break is when? Okay, we'll discuss it.
25th.
Yeah, I think I took the long, but we'll discuss it. We don't have time anymore. Okay, we'll discuss it next meeting. But the class time before the semester break, we'll have our long test one day. Okay, you have everything already. You can make a advanced study if you want, so that you don't have to wait for me. Okay, and so that anything else I can just put on top of what you've learned already. But otherwise, you can wait. That's fine. But be ready. That will be our long test one. If necessary, definitely I will have a class before that. Okay, the lab time before that, I will have a lecture like this so that I can answer your questions. Okay. Okay, so we agree lecture class during lab time will be 1 o'clock. Okay, lecture class during the regular time will be regular time, 11 o'clock. Okay. Okay, thank you guys. See you. Okay, bye. See you next meeting.